So it's a pleasure to introduce Ernesto Lupercio from CINVESTAV, main organizer. So he'll speak about string motifs and the number 12. Ernesto.
Thank you so much. Well, it is a pleasure to be here. I'd like to tell a little bit, just a funny story, you know. It is a very light talk. The void of complicated things is just fun. And in this divertimento, I will explain that there is a story that mostly Bernardo and I, and of course Tommaso de Farnex from Neuvns started developing. It's been dormant for a little while, you know. Then with Enrique, we have reawakened some of these themes, and with Ludwig. And you can see in the video the talk of Enrique the part of this story, and I will give a little bit of a complementary part of the same story. But I think the number 12 recently has provoked a reawakening of an interest in several threads that were kind of loose. And now the number 12 seems to be telling us what to do. So let me tell you, it's just a fun story. It's nothing elaborate. Just to relax at the end of the day. Anyway, where we're orbifolds, but of course, you may want to think that an orbifold, if you want to ignore everything here in this slide, you just think that an orbifold is a manifold divided by a finite group. And all this slide is written just to convey that this is, if you want to be precise, only locally true, but not necessarily globally true. We have these kind of charts that look like manifold divided by a finite group. Another slide is just to convey that you can really pretend that it's just a manifold divided by a finite group. And so, what is the correct notion of a vector bundle? Well, the correct notion of a vector bundle is the equivariant vector bundle. So that, for example, if you have a vector bundle over a point in this world, is a representation of it. So vector bundles come together with representations of the local isotropy groups of the atom. So it's a generalization of the notion of the representation. So a vector bundle over a manifold that has a DG action. Well, it also has, especially at these points, if H is the stabilizer here, well, then the fiber is a representation of H. You have all these, you imagine this vector bundle of representations of the local stabilizers of the groups going around, and so on and so forth. And in 2004, Bernardo and I defined a particular kind of K-theory for these orbifolds that was very simple-minded kind of notion of K-theory. But recently, Enrique and I have proved that this was always the correct notion of K-theory, and you didn't need to do anything more complicated. People did more complicated things, but then recently we managed to prove that Pardon first, and then Enrique and I, by a very different method, have managed to prove that it's really the correct notion of K-theory, that you didn't need to do anything more complicated. So either by the method of John Pardon or by the method of Enrique Becerra and myself. Okay, so that's, you form a K-theory out of these equivariant vector bundles if you are thinking that the quotient is equivariant K-theory, nothing else. Everything else equivariant K-theory. And so let's consider now a remedial metric on the manifold. And there is this family of operators on the K forms called better. And of course, these operators are the avatars of quantum. There is not a topological quantum theory, but nevertheless a quantum field theory associated, whose semi-classical manifestation will apply. In the case of Lagrangian, for the quantum field theory is given by these formulas, that is simple as it gets for Lagrangian. And all the information of such quantum theory is contained in the spectrum of the Laplacian. I mentioned spectrum, but different spectrum. So all the information, but not so different spectrum you think about, but that comes soon. In any case, recovering the classical theory from the quantum theory is here in the shape of the drum tradition. So, and of course, the whole story is here in the shape of the drum kind of thing, but you do lose a little of information from the classical picture to the quantum picture. You could copy slightly different classical pictures that correspond to the same quantum picture, at least the origin of all these so-called dualities. In any case, the Feynman functional integration approach for their theory allows to compute the integral over the free loop space of the manifolds by stationary phase approximation of an integral over just M. By stationary phase approximation, because the Lagrangian oscillates rapidly. In any case, the heat kernel approach, this equation, quantum field formalism, it relates your story to the heat equation under weak rotation. And so you solve the equation, just a linear equation. And the fundamental solution for the trace of the heat kernels is given by this integral here to the -1 times the Laplacian, where h bar is meant to be e to the -1. So I'm trying to say the role of the constant is taken off by t to the -1, and then we have that the trace of these operators is. And in this case, if you're in the one-dimensional situation, these actually can be done within the bigger measure, only in the one-dimensional situation, not in any other dimension. It turns out that the sum of the traces of heat kernels is independent of t. This is the usual trick. Witten does it very often. And the long time limit of this sum equals the Euler characteristic. And by recalling Hodge's theorem, which identifies the k-Betti number of M as the dimension of the kernel of the Laplacian, the harmony forms, and the short-term behavior is given by an integral of a complicated curvature expression. So, but we have then one side is the integral of a curvature expression, and the other one is the sign sum of the Betti numbers. And we know what that is. We recover the Gauss-Bonnet theorem using this Feynman integral approach. And why would I do this very simple-minded thing? Well, because we're tired one, but the other reason is that this is the manifestation that motivic measures can be written as Feynman integrals. And so it is a convenient yoga to try to find which is Feynman integral will be which motivic measure. It's a useful yoga that is a yoga that we're going to try to do.
But you're thinking about these propagators when you mention this kind of integrals, like inverse of the analytic operators.
Well, you see the propagator is e to the minus c delta k.
Yeah.
So, but yeah, why not? Anyway, we're getting motivic measures equal Feynman. Measures equal Feynman. Okay. We have oversimplified, of course, and we can do a little bit better than the Euler characteristics. We can do all the motivic measures. In fact, we can do even a little bit better than just motivic measures. We can combine them into some sort of general kind of thing. In any case, if M is a spin manifold, we can recover the index of the Dirac operator using the loop space. But let's go back to the orbifold case. I did this on the manifold case, but we would like to do it on the orbifold case and maybe ask, what does it say? What is this relation to groups? What is the relation to these symmetries to the story? And to apply these methods to an orbifold, we have to say what is the loop space of an orbifold. And this was developed by Bernardo and myself. The idea is that to a groupoid we must assign a loop groupoid. We were talking so very much about the loop group in the talks, this conference. Well, this is kind of a generalization of the loop group called the loop groupoid. And our construction, and this was proved by Uribe to protect itself, there is these two functors, a loop groupoid functor that applies to a groupoid, or the loop stack functor that applies to stack, and the classifying space functor B, and they connect. This is a theorem of Bernardo, Miguel, and myself. So BLX is LBX. Okay. So what does it look like on the chart? Well, on a chart it looks like this. We have the objects of the loop groupoid are paths that start at X and then at GX. Not quite at X, but at GX. That is the same point of the origin. And then it has a natural accident G, and that's the local chart for the loop groupoid. And it is written here in detail, but it's what I just said. This is what it is. This is a loop in a global orbit, let's check. In the chart of course, I could be long. I may have to jump from chart to chart, but to be a long loop. This short loop. In any case, we have this loop stack or loop groupoid associated to an orbifold or to stack. And the orbifold localization principle of Bernardo and myself said the following. Traditionally, if you have the loop space of a base of a manifold, well, it's you can then rotate the loops, can't you? So you have the loop space of a manifold would be the loops in the manifold, but then you could rotate the loops and you have a S1 action on the loop space. And clearly the points of the S1 action are the constant loops. Are the constant loops. This is very clear, and it also happened in Eduardo's talk. So now what happens for SAT? Well, for SAT, what happens is that the fixed points of the structural action in the loop orbifold is not the orbital, it's the inertia of it. And this is our first theorem. This very basic principle is what we call the general localization principle for orbital theories. And from this, very many general orbital expressions can be deduced, as I will explain. What is the inertia? Well, the inertia is, well, you can think of it as the automorphism of the points are the objects now, and now the arrows are the conjugations. And this is the inertia of a. So, for example, if you had just a final group acting in a form, you would end up essentially with biconjugacy classes of the group as the inertia. So that's what it is. That's the localization principle. Now the constant loops are no longer the orbifold. The inertia of the orbifold. Of course, the inertia of the orbifold is just the manifold. That's what you don't see. But then this is where they make the inertia appear all over the place in quantum theories, like the ones described in the. And this answers a little bit the question that you asked me earlier today. You could have the fifth operator, but now you have the inertia in the shift operator.
Just to be sure, you are always thinking of an orbifold as a group point.
Well, no, not really. I mean, I'm thinking of an orbifold as a stack. And a group point is an atlas of stack.
Ah,
But you don't need to say the rules. You may think there is a rule. Okay. So again, this I already said. This is what happened for manifolds. But for an orbifold, you have this kind of new things appear out of nowhere. And therefore, just from this fact, we expect the Euler characteristics, the K theory, and so on and so forth, to localize in I of X rather than X, according to the principle of Bernard and I proposed back then. And the orbifold I of X is called the inertia orbifold in mathematical literature, and the physics literature is called the twisted set. So it has two names. And the localization principle justifies to call invariance restricted to I of X as stringy. For the twisted sectors appear right before the inertia stack in the famous paper of Dixon, Harvey, Barber, and Wiley. So that. In any case, for a general orbifold, the so-called orbifold Euler characteristic can be defined in many ways, and Conway's definition is very pretty, but it's just the Euler characteristic of the inertia stack of the orbifold. So it's the same thing to compute one thing as to compute the other, of normalization, because by the order of the group or whatever. Let me just be exceeding the character about this stuff. I have to get at 12, so happy. In any case, we have Seagal's localization of K theory that tells you that equivariant K theory localizes to the inertia, which is by Graham Seagal's K theory arguments. And if you have a global quotient, then this is what explicitly, and you've seen this formula appearing in all sorts of places, the inertia stack will look like. It will look like this for a global chart. Very good. And this covers the Seagal localization on the previous slide. So we defined the Gauss loop space, LLDX, as the subspace of elements. You see, now you do the classifying space. It's no longer an orbifold, now it's a topological space, and actually a homotopy type. So you have your orbifold, and then you get a classifying space. And what this space looks like more or less is here you have the quotient space, just the topological quotient space. And at every point here, if you have a point X with a stabilizer Gx, this fiber here is Bgx. And of course, it's not a vibration, but something more complicated because the fibers jump all over the place according to certifications. There is quasi-vibration, but this is relevant. The fibers are different at every point, just the classifying space of the stabilizer. And that whole thing is called the classifying space of the orbifolds. That's the classifying space of the orbifold. It's topological, it's a homotopy type. And now we define the Gauss loop space as the loops here. There is loops here, and this loop is not in the Gauss loop space, it's just a crazy loop. But if I have a loop that does, it just lives inside here, it projects to a point, call it a Gauss loop, because I don't see it in the quotient space, but they are there. And this is the Gauss loop space. And the Gauss loop space is the classifying space of the inertia stack. These are the things that we proved in our paper on Gauss loop spaces. And well, the Euler characteristic is 3. Okay. So let's consider a classical example of Kleinian singularities. This is, let me take the simple case, the AN singularity, or called AN singularity. There you have the G invariant polynomials. And we can resolve very easily singularity by R minus 1 blow ups. And there you have the exceptional divisor. The incidence graph of the exceptional divisor is as boring as it gets. It's R minus 1. You get this incidence graph of the resolution of singularity, the exceptional divisor. On the other hand, G has clearly R minus one non-trivial irreducible representations. And so this is the Mackay correspondence. This established among many other things a one-to-one correspondence between the number of components of the exception device and the minimal resolution of the singularity and the number of non-trivial irreducible representations of G. So that's the story. And notice that from what we have said, this story that we have to start, we said in a little quick, but nevertheless, we can deduce immediately the statement that the orbifold Euler characteristic of X is the same as the ordinary Euler characteristic of Y. So the inertia, on the one hand, you have the inertia, that is the Gauss loop. You have the Gauss loop. On the other hand, you have the resolution of singularity, and the two things compute the same combinatorics. The resolution of singularity and the Gauss loop space. And well, this suggests that we could have a final integral approach to the Mackay correspondence. Well, we can do even a little bit better than our colleagues than integral approach. We can do a little bit better. We can take this reverse version of, when you assume localization, you could really think about integrals that are almost localized. But now now logic enters into the picture. And now you are working in the language of generalized sets and so on and so forth. And now the natural place to land is in the motivic ring that has been described more than one talk at this conference. So we can do motivic integration, and this was discovered by Maxim Kontsevich. So rather than thinking about literal loops, because they are very, very small, you can think of very small loops. Because you're localizing the integral anyway, that thing will go nowhere. It will be highly oscillatory, you throw it out. You take these very small loops, and now because they are very small, they can be extended holomorphically. And well, now you think of maps from spec C of T to Y. And you call this arc space. Because now you're using a different analogy in your mind. You call it arc. Because you think of C of T as a little segment. But one thing is kind of orthogonal to the other. When you call it arc space, you're thinking of this segment. And but it's a small loop, you're thinking of this little boundary. In any case, you call it whatever you want to call it, but it's what it is. And that's the thing. And it's the inverse limit objects of all these, the pro variety. And these location maps are important to find the measure. And divisors can be thought of as an integral for loops. How do you transform a divisor into an integral? Well, for an effective divisor, one can define this order with which to each arc associates its order of contact to D. So to each arc, it associates the order of contact. I mean, this is what you are going to integrate. So we want to integrate these functions in some reasonable sense, but the value of the integral will not be a number, will be an element. So well, we do these cylinder sets, and we do the motivic integration. So how do we do? We fix a complex variety and assume that Y is an X variety. And now we'll do it deliberately in the relative case. Not only I will integrate these functions into the variety, these loops, the space of the variety, but I also deliberately do it in the relative sense with respect to X. And I can do it, we do that. It's the same as Enrique was talking about, and some other people were talking about during their talks. But I do it relatively to X. I just do it relatively. I just do the same. 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 This is standard approach. So relatively.
In
more standard language, like think of space change.
That's right.
Yes.
That's right. So everything comes with a map to it, so our varieties over X or yes. Of course, I can tell you regular commands over X and what it changes.
I mean the division, the concept works the same way.
Yeah, that's right. So it's the same thing that Enrique was talking about, but relative to X. And then I said the measure of a collection of these loops is this motivic class by this normalized divided by L to the N to normalize and so that it has the correct measure that one would like to have. And then one can integrate, do this final integral that is called a motivic integral. Notice that the Lagrangian becomes a part of the divisor of the electric motif. And now, but there is a remarkable thing, and is that with these definitions, one can prove that the answer is combinatoric. So the integral with this measure becomes this combinatorics on the exceptional device. The integral is defined without resolving singularity. But if you resolve singularity, you have a combinatoric answer to your integration.
Let me ask you something, perhaps in sense, because you have this formula, and then I can see, I even understand this L minus the order as some kind of propagator. So in the sense that it is the inverse of something. So my question is, if so, what is this something? Like, what is the corresponding elite operator?
Well, you see.
Okay.
So you do this thing. And then there is a change of variable formula by Maxim Kontsevich that says that gives you how is it.
So is that thing like an inclusion exclusion?
Yeah.
Okay.
Yeah. And then you do this, you get the formula by Maxim that tells you what to do when you have a simple normal crossing resolution. And so it tells you how you change the thing. And notice that the universal thing is the Jacobian is the canonical case, the relative case. So that tells you the change of variable formula. And it can be extended to singular varieties. And you need to do things. They can be done. And this was mentioned somewhat by Enrique in his talk, but the resulting measure is called the Gorenstein measure. We write it. Enrique was writing slightly. So the motivic Bakai correspondence. This is a technical thing. I'm going to identify a tile exchange for things to work out. Because otherwise I will be read it. Forget about this. But anyway, we have the correct motivic ring, and we do the initial completion as Enrique described in his talk. And notice that if X is a point, this tile by exchange goes up. So if X was a point, we are really in the same framework what we used to be, but that is not a point that we need something very mild modification. Okay, so if we have that, it turns out that you can do the combinatorics by the Bakai correspondence and the motivic integral localized to the inertia. This is what formula 11.1 says. So it localizes exactly the same as the final. It's telling you that the integral over the whole thing localizes to the motif of the inertia. Just by the combinatorics. This doesn't use the change of variable formula. It shows the combinatorics. And well, now let's play a little bit. The other characteristic defines a ring homomorphism from motivic rings to the infinite. But now we are in the relative situation. In any case, just this formula here, because we are in the relative situation, already implies the Mackay correspondence for relative characteristic. That's because in the language of X, in the topos of X, this is situation is the point. So the point is the Mackay correspondence for relative characteristic in the topos of X. And this is just the counting statement. There is more information we could try to recover it by this motivic integration method. In any case, well, this is a proof, but I'm really should perhaps given that let me just say very quickly that well, this is really seeing the inertia star as this small Gauss loop space. If you think of the inertia star as this small Gauss loop space, then you see these arcs lifting the connected components, and then you do the combinatorics, and then you get the proof. So let me note. Paquetito le ayuda, and voy a recordar myself, extended this argument to deal with the Stringy stuff and understand how they change under this kind of birational resolution. How the canonical device changes the Stringy stuff. Well, this is going to be important, very important for the number 12. So let me just mention that. You can go to the characteristic, and this is the classical. But you could think about the E polynomial that is made with the cost. That it would be set of UB rather than Z. And if you do this very carefully, and blah 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 blah, then we managed to prove for the all the structures themselves, K0 K. But if you want for the E polynomial or the Hodgson E polynomial of the orbital. So the Hodgson E polynomial of the orbital behaves has mechanical properties. Hodgson E polynomial has mechanical properties. Okay. Well, you can keep playing a little bit with this. Why not? What about if you use now you use a field that is a relative situation, and what was a number now becomes a function. What is a number in the topos of X? Well, it's a function of X. And the right to consider constructible functions of X. Because we are in the language that was being explained by Carlos yesterday. So in the language of X, we end up with a construct, with a one that you can define in semi-algebraic sets. So you end up with a constructible function. And then, well, you now you really work on it, and you work with the Euler characteristic. You do the Euler characteristic argument for really relative. Now it's not a number, but it's a function. Okay. So, but there is this functor, this universal functor from constructive functions to the child group. It's a universal functor for from constructive functions to the child group. And the universal functor was conjectured by Grothendieck and proved by McPherson that is the same as to have the Schwartz templates or similar. So there is this natural transformation from constructible thinking, that is numbers in topos of X, and the child group of X. And this natural transformation is the universal natural transformation in the Chern class, the total Chern class. And this is but you see, you cannot see it during the function one, isn't it? We should be studying the function. You use the function one. you get the total classical Stuart McPherson graph. But obviously, this is the wrong function to use for an orbifold, isn't it? I didn't just say that we should use the function of the inertia track, not on the stack. So when you do it, you take the relative canonical and you do the mobility integral of that. No, for a manifold is one. For a manifold is no. It's kind of one in the inertia, it's kind of a different thing. You do it. And you define the Stringy class. And then you prove what I just said. That the Stringy class obeys the Neuvns and Uribe localization principle, and you get this one. So this is the correction class. If you want the right mechanical response by rational, correct by rational invariant. The other one is terrible for rational transformations. Does nothing for rational transformations. It's done wrong. So this is the correction class, isn't it? So we call it the Stringy class, and this is the word with the Farnex and Neuvns. And then, well, now we have, of course, it implies again the other characteristic, Mackay correspondence, but now it has a much stronger version of Mackay correspondence. If they are K equivalent, namely, if I have these two resolutions, and if I pull back the canonical divisors and the subtraction is 0, they pull back to the set, then I call them K equivalent, these two varieties. And so this is a much stronger version of Mackay correspondence, but it is different that from what I said. And well, in this case, we show that then the Stringy class invariant under this kind of transformation. So it's the correct notion of Stringy class. Correct by rational geometry, this is the correct notion of Stringy class. But of course, notice that is defined an integral. This class is defined. All I'm saying is that on the dimension transformation, in the language of the topos of X, the correct notion of Stringy class is defined an integral. In the language of the topos of X. We're getting almost to number 12. Okay. So, well, let me go rather quickly about this. There is, we want to go a little bit further. We have to review what Witten and Pilla did for the index of the Dirac operator and the actual quantum field theory that were shadowed and very geometry by rational geometry. So we have this compact symplectic two-dimensional manifold with symplectic form, and a Hamiltonian, and the critical manifolds, and the Liouville volume form, and we have the Gaussian form. You tell me I'm right.
Sounds familiar.
Sounds familiar. And it alpha is the equivariant Euler class of the normal bundle, the 6 points. Yes. And this is the basic localization for a Hamiltonian measure. Okay. H bar is taken as purely imaginary, the integral is oscillatory. And the submanifolds are the stationary points of H, and the right-hand side of this formula is given by the stationary variables. And this is very related to my talk in Solid Beach a few weeks ago. In any case, we use the idea of using Deutzer and Heckman. Well, this was for a manifold N, okay? But now you take, of course, the loop space of N. And I take, of course, the loop space of X, not N. But let's do N. If we do N first, and we take the Hamiltonian for the quantum field theory, and Atilla did the calculation, you know, when N is spin, Ln is oriented. So that's why you need a spin element for the index of the Dirac operator. Because when N is spin, to say that N is spin is the same thing as to say that L operator is oriented, and you want the N oriented. And now you do the, so you do the stationary phase approximation, and it turns out that this side gives you the index of the Dirac operator, and this side gives you the A Hagibus, and you prove that yes again and so on. So this is exactly what you get. You get a proof of what Atilla used to call a postcard proof of the Atiyah single in the formula to write on a postcard, send it to the friends. When there were postcards. Now, Tommaso, Tom, Bernardo, and I said, well, let's put X rather than N. And let's see what we get. What do we get? This is not terribly surprising. We get the Kawasaki, the orbifold Atiyah single in the formula, but we do. Blah, 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 the loop orbifold, we have the loop stack, and then we do the normal bundle, and then we consider the Euler class of the normal bundle, and then we take the time and space, and we do the Fourier approximation of the time and space of the normal bundle of the inertia stack inside, because it is the constant loops in the loop stack. We take the inertia stack, and then we do the loop stack, and we take the that, and we do that, and we keep doing that. But then at some point, when we compute the eigenbundles and all that, at some point we get this kind of funny formula that diverge. And then, well, we just say, well, diverge renormalization, theta function renormalization. We just do theta function renormalization. Because the formula all the nodes diverge. But as you know, 1 plus 2 plus 3 plus 4 is equal to 12. Well, because we did 12. Anyway, we do the normalization here. And then we do the theta function renormalization. And we get the formula that appears in Atiyah single. We get the Atiyah single formula for the equivalent index of the Dirac operator. So that's very nice, and it localizes to the inertia stack because of that we said. We get the whole thing. Now, but then why stop there? We said. Obviously, now we have to do this on the loop space of the loop space. Of course. I mean, why would you stop there? You know, you can keep having fun. You know. So if you do it for n equals to loop space, then you get the Atiyah single in the formula and the orbital version, the equivalent Atiyah single in the formula, the Kawasaki formula. This is for n equal to. But now, why would you stop? Now you do the loop space of the loop space, but of course this is a space of mapping from a torus to M. And now we know here that we have this is SL to Z. And now we have the, well, this torus mapping into M, space of all these maps of the torus, but they cannot be just maps from the torus well. They have to be stacked maps. Just like the loop report. Now you need the loop report of the loop report to the very thing. But you do it. And then you do it, you do it. And then will be many more slides. But I'm not skipping all of them, and you use things, and you all again use theta function renormalization. You get divergent expressions. But you think of them as formal, and then you use theta function. You change the you change the function of the theta function, and then you use theta function renormalization correction, and then all of that. You get the elliptic fields. Now, this is very interesting. From what I just said, it can be deduced that if you get the elliptic genus, you evaluate at certain values, you will recover the simulation flex. So, and of course, from what I said, one can expect, and we want to prove that there is an actual version of the elliptic genus, and that this can actually be done with actual logarithmic integration rather than with theta function, the normalization final integrals. Nevertheless, with theta function and normalization final integrals, we get the expression. It's a long calculation, but it can be done. And one can use the device to recover the two variable expression for the elliptic genus. So that's, and this is the G elliptic genus, that is a much more complicated problem. And in this G elliptic genus, you find the spectrum of the singularity. So we recover the spectrum of the singularity from a double loop space integration procedure. Okay, the number 12. Let me conclude this story with the number 12. There is this classical paper of Punen and Rodriguez Villegas that says that you have a convex lattice polygon. So you take Z mod 2 inside Z2 inside R2, and you take these lattice polygons, and you take convex ones, and you make sure that there is that the only point the lattice inside the polygon is 0, 0. Otherwise, you scale. You take the make sure of that. Then the measure of 1 plus the measure of the dual is equal to 12. It's a very classical paper called Lattice Polygons and the number 12. And here you have an example. P1, P2, P3, 5, Q1, Q2, Q3, Q5, and 7 plus 5 is equal to 12. So this is a beautiful classical paper. And they continue this from the paper, literally from the paper. To one who specializes in algebraic geometry, 12 might be the number appearing in Euler's formula. 12 is 1 plus PA equals K squared plus C2, which relates certain invariants of an algebraic surface. This formula is a special case of the Hirschfeld-Riemann-Roch formula. That is a special case of the Atiyah-Riemann formula. So this is a special case of the Atiyah-Riemann formula. And the 12 comes from the expressions in the integral that I displayed before. It's the same 12. And it's the coefficient of x squared in this multiplicative series. This is meant to be for the continuous. This is meant to be the series for the continuous in characteristic class. In Chern class, x is meant to be Chern class. And then you get the 12 as a Bernoulli number. But then you get all the numbers. But 12 is a signature that something is going on. In fact, using this fact, you can prove this theorem. And maybe beautifully. Using this fact, you can prove that theorem. That's 12. To one who studies automorphic forms, 12 might be the weight, which is the cost of the smallest weight of x to z. And again, now this 12 comes from the double loop space in our picture. And it's the 12 integral that we perform in the localization principle for the integrals. And they also prove this statement from that 12. They prove that these two 12s are the same 12, not different 12s. They are the same 12. Finally, in astrology, 12 may be the number of signs in the zodiac, but this has nothing to do with it. No. No. The point of the third remark is that there is 12 and 12s, but these 12s are the same 12. You can theorems relating one 12 to the other 12s. Okay, so a paper on September the 5th, 2023, I found it very interesting, is about LVP log del pezzo polygons and the number 12, repeating. It's the same 12. And 12 is the same 12 that Shkolnikov and I, Michalki, Stolnikov are considering to pi in certain contexts. The same 12. In any case, Booking, Hasse, Staller have this number 12 revisited. This is the inductor is the old 12. Except that when they say L, you start realizing because you don't want to use half integers, that you don't want to use the area, you want to use twice the area. That's why they have 12 here. And here in the abstract, they don't want to get people confused, so they write area and they have 6. But this is 12. And in case, in this paper offers a combinatorial proof of the combinatorial identity, that is a generalization. It's now no longer for this very specific only one point inside also, but there are many of them now. with a very high condition. There's a lot of them. Notice that in our paper with Tommaso and Thomas, we have to use log term singularity to make the thing work. And it's the same situation here. It's the same, this is the same log, the log in our paper. And in any case, here you get 12. If you use twice the error, you get 12. Some interesting, it's a generalization that tells you how to correct the formula for more polygons, but it's still the 12. But my punchline is that this 12 is a Stringy rules. It turns out that this formula is equivalent to this formula at the top of this page that says that the Stringy chain class, the second derivative of the Koch-Delin polynomial is the Stringy chain class, but the factor that relates the Stringy chain class and the Koch-Delin polynomial is 12. And this is the same 12. This formula is exactly the same as this formula. And so that's where the 12 is coming from. But because this is a limit on the formula for the elliptic genus according to what I said, this formula can also be written in terms of the elliptic genus, and in the 12 from the elliptic genus that we're witnessing. So, and in the elliptic genus is written in terms of the spectrum. So this gives a new proof of the variance equals to 12 for the spectrum of certain singularity. Complicated proof, nevertheless an proof. But it's very intriguing what this, the proof is a signature that we have an interesting relation here that we have to understand. And that's all I wanted to say today. Thank you very much.